In this third question, it started out with a mass spectrum. This is mass spectrum of this element magnesium. The fact that we see 3 lines, 24, 25, 26, and each of them have their own relative abundance. This must be 10 because there was 50 there. So 10, 20, 30, 40, 50. And that thing is just below 90 there. I think it's 90, 60, 70. Oops, I was wrong. That is not 90. Do not make my mistake. Oh, excuse me. So there was 50, which means it's 60, 70. So read that carefully. There's 80 there. So that's just below 80. And this is just above 10. If you look at that carefully, this is 10%. This is just above 10%. So without wasting so much time on it, I will just say estimate probably say 11% or 12. And this is going to be the difference there. So the difference there is just going to be, I don't know, 79% maybe. 79% if you're talking about 11%, or 78% if you're talking about 12% there. And you can see the percentage will add up to 100%. Of course, 79 plus 10 plus 11, 100%, or 78 plus 12 plus 10, that will give you 100% as well. So from the mass spectrum, complete the table with the relative abundances. So there's a 10% there. I think I'm just gonna stick with that looks more like 78 because it's a bit lower. But again, you don't want to spend too much time thinking about, 79, 78. At the end of the day, they're going to be roughly approximate unless they give you the value there. So the 26 there is going to be 12% if I use 78% for the top one there. Now use your values to calculate relative atomic mass given to 2 decimal place. And they are very stingy in A2 because they expect you to be able to do these kind of calculations in A2 already. The mass number multiplied by the percentage, so 24 multiplied by 78%, and then you add up with the other multiplications of mass number and the percentage, and you add up the other one, and then that whole thing in a big bracket. Make sure you use bracket to be careful. Divide that by 100%. What you will get then is 24 times 78 plus 25 times 10 plus 26 times 12. You get 2434. And you divide that by 100%. So you get 24.34 on your calculator, and that is exactly to 2 decimal place on the calculator. So I'll just leave it as 2 decimal place as it is there. If you look in your periodic table, you will see that this value is not very different from the one given in the periodic table because it's supposed to be very close to the 24.3 in the periodic table that you are given in exam. But of course, we cannot write 24.3 since they want it to turn 2 decimal place based on our calculation. We are just confirming with our periodic table that our value is definitely correct there. In this next question, this is about a fixed essay for these 3 marks. It's a fixed essay because you can definitely prepare for this. Thermal stability of the group 2 nitrates. In the new syllabus, in the new specification, they will have changed this Roman numeral to this number here, group 2 nitrates. And it's the same trend with the thermal stability of the group 2 carbonates. So we just need to be able to prepare our essay. So first of all, actually, I'll probably explain first because it's a lot easier to explain first. Down group 2, what we can say is there are more filled electronic shell. So there are more electron shell essentially. There are filled. And as a result of it, we can get a bigger ionic radius. So ionic radius of the M2 plus cations, because we're talking about general group 2 cations, and these are nitrate, which is NO3 minus. Even year 9 student is expected to know the formula of nitrate ion. Ionic radius of M2 plus cations increases, the size gets bigger, but the charge is the same. So the charge remains plus 2. Overall, what you can say is the charge density, because charge density is to do with charge over size. So what you get is charge over size. Your charge is the same, but your size is getting bigger. So what we can say is, therefore, the M2 plus cations become less polarizing, or we can say the M2 plus cations are less polarizing on the anion, on the NO3 minus anion. And what does that mean? That means the NO bond become less polarized, and therefore it is less weakened. If it is less weakened, it means it is much more difficult to break. Therefore, much more difficult to break. If it is becoming much more difficult to break the NO bond, what we can say in the trend is the thermal stability. How stable is it to heat? The thermal stability of the nitrates will increase. It become more stable to heat. So of the group 2 nitrate, M2 plus, NO3 minus, so it's MNO3 twice, it will increases. Sometimes the question can change to temperature of decomposition. So the temperature required to decompose it will be much higher. Sometimes they can talk about the ease of decomposition. So it becomes much more difficult to decompose. So the ease of decomposition would decrease. Just playing around with words based on this last sentence here about the trend there. So I already described the trend, but I explained first and I described the trend because I find it easier. But whatever you do, doesn't matter the order, you still have to address both parts of the question for that full 3 marks there. What do we have in the next? We have the question, lithium nitrate. So you decompose lithium nitrate, you get a brown gas. The fact you get a brown gas, that means you get NO2 gas there. So very similar to what happens with group 2 nitrate, because what happened with group 2 nitrate when you decompose that, you will get the group 2 oxide, M2 plus or 2 minus, that is your solid group 2 oxide. You will get 2 NO2 gas, which is brown in color. You would also get a colorless gas, which you don't see, of course, because it's colorless gas. So what do you see? You don't see it. You just test for the gas. When you see the brown gas, you also need to test for the oxygen gas if you're doing this in practical. The ratio matches because 2 nitrate, they give you 2 NO2, and then this 1 oxygen, 4 oxygen, 5 oxygen. You have 6 oxygen on the left. You just need 1 oxygen atom. But oxygen exists as a diatomic molecule, you must have half of it. Some teachers would say, write down 2, 2, 4, and 1 is perfectly the same equation, just divided by 2 there. Here, we don't have a group 2 nitrate. Instead, what we have here is the decomposition of lithium nitrate. And it says it follows similar kind of chemistry. This is Li plus because group 1 metal ion, NO3 minus. You're going to get lithium oxide, Li plus or 2 minus. So you're going to get 2 of that Li plus to balance out the charges of O2 minus to get the formula there. You will get a brown gas, which is NO2. And it's similar to that happens when you heat up magnesium nitrate, but it does not occur with other group 1 nitrate. So I'm going to assume that it also gives oxygen gas. And let me see if I balance the equation. 2 lithium there, so 2 of that nitrate. 2 NO3 will give me 2 NO2. And now what I have is 1 oxygen and 4 oxygen. So there's 5 oxygen. 2 times 3 is 6 oxygen. So again, I have this issue here where I cannot change the formula of the molecule, but I can change the number in front so that I have 1 extra oxygen, 1 oxygen atom, 4 oxygen atom, another 1 oxygen atom, altogether 6 oxygen atoms. 3 times 2, 6 oxygen atoms there. Very last bit of this question. Suggest why the group 1 nitrates other than LiNO3 do not decompose in this way. Do not decompose in this way. Well, what is so special about lithium? If you look at lithium and then you have that staircase relationship, so I think that this relationship is no longer that relevant in the new syllabus, but it used to be stated that you need to know something called the diagonal relationship. So it's the same thing when you have boron and silicon. So boron and silicon have similar kind of chemistry, and then you have aluminium just below boron, and then what we say is beryllium and aluminium. Beryllium and aluminium has similar kind of chemistry. So I'll give you an example. Al2O3 is amphoteric oxide. Now, all of the group 2 oxides are basic except for beryllium oxide, which is amphoteric. And why is that? There is such a thing called diagonal relationship. And where is the origin? What is the origin of this diagonal relationship? Well, like I said, it's no longer that relevant in your new syllabus, but then this diagonal relationship arises as a result of very similar electronegativity. Actually, it might still be asked in your new syllabus. If you look at AS chemistry, if you look at the new syllabus, AS chemistry, they can give you electronegativity values. This is stated in the 2022 syllabus where they are expected to be able to use electronegativity values, and if they have similar electronegativity values, when they combine with oxygen, their property is going to be similar. So I stand corrected. I think it could be asked in the new syllabus as well. So we can say that because of the diagonal relationship, so that means only lithium has a similar electronegativity. Do I want to say this? Only lithium has a similar electronegativity as magnesium. Therefore, lithium nitrate follows not just lithium nitrate actually, lithium chemistry, lithium plus chemistry in general shows similarity or resembles to that of magnesium, the group 2 metal, to that of Mg2 plus metal there. Okay, so hopefully that makes sense there. But of course, this is not for the group 1 metal, this is for group 2 nitrate then, group 2 metal nitrate decomposition in the presence of heat. Not too much you can write for that 1 marks, but it's definitely to do with diagonal relationship and similar electronegativity, therefore similar chemical reactivity as well. And that's the end of that 7 mark question there.